So I'm going to talk to you about the Intel MPI for the mic at this point. The obligatory legal notice. Yeah. And my own disclaimers and notices. I'm not an Intel employee. I'm not compensated by Intel, and I do not speak for them. If I get something wrong, don't blame them. Okay? Also, if I've annotated their slides with additional content, I've denoted it with the little Nix icon. So, brief overview to start with. We have the typical view here of the tools that are available. You know, traditionally, Intel has supported the multi-core and the cluster environment with a very robust set of tools. And now they've done exactly what you'd hope they'd do. They've extended those tools to the mic, and they work the same way across all the platforms. Okay. Now, perhaps I should say, by release, all of the tools will be extended to the mic. Right now, there's a very, very functional set of them. So what does that really mean? Well, that means if you're using C or C++, you have access to things like Silk Plus, the thread building blocks. You have your C and C++ compiler that you're used to. OpenCL will be available at some point. OpenMP is there now, and you have the offload pragmas that they provide. So Fortran, you have your compiler, you have CoArray Fortran, offloads, and OpenMP. Is CoArray actually in place now? Okay, it will be. Okay. Silk is C++, not Fortran. Yes, as is TBB. And the common link here is that you have Intel MPI and MKL for both Fortran and C and C++. So the MPI library from Intel, it's actually a very nice implementation. It's optimized for most of the applications that you're going to run across. And it's low latency, interconnect independent. Currently on mic, it's got support for the latest, it's got OFED support in place. We'll talk about that in a minute. And it seamlessly interoperates with their trace analyzer and collector so that you can do some pretty sophisticated profiling. So current clusters are not homogeneous with regards to speed. We all know that. You have internode issues with the network, and then you have intranode issues, both between sockets and between cores, potentially in the processor. Well, now we've added the mic to this, and the mic is, of course, sitting across the PCIe bus. So you've got two different other types of communication to worry about, the host talking to the mic, and the mic can talk directly to other mics as well. So, and they'll all have different speeds. So how does the MPI library go about determining what driver, what interface to use to communicate across the networks? Well, you have this IMPI fabrics that you can set explicitly, or you can allow it to search. It will typically look for the InfiniBands first because they're the highest performance, the RDMA. On card, you'll always use a shared memory interface, and then it'll check for the DAPL, the OFA, and the TCP is the fallback. And that's implemented over the virtual Ethernet stack at the moment, right? If I recall correctly. TCP is, yeah. So let's talk about the programming models that MPI enables for the mic. We have a spectrum that ranges all the way from completely running on the Xeon to completely running on the mic. Okay. If you've got a largely serial code, you'll want to run on the Xeon. Well, the next stage over, you can offload highly parallel phases. Okay, and you had a session on offloading yesterday. I'm not going to go into a whole lot of detail about it. But you know, in that sense, you run on the MPI rank and it offloads to the mic. Okay? You have a Symmetric, which Intel uses for a balanced view. And I inserted this reverse offload, which at one point later on I also refer to as an asymmetric case, in which essentially you can just throw MPI ranks across all the devices, coprocessors and sockets, you know, or nodes if you'd rather work at that granularity. And then, you know, if you're using a single program and treating them all the same way, then you end up with a symmetric case. And if you decide to differentiate based on rank or communicator or something like that, then you can end up with an asymmetric case, which is what the reverse offload is an example of, where you might be running almost completely on the mic, and decide that you want to handle things like file I/O on the processor. So as an example, for the Boltzmann solver we looked at earlier, right? It's highly parallel. There's no reason to really worry with the Sandy bridge unless we want to start doing interesting things like pre-processing for additional steps or post-processing results. So at ISC we actually had a demo where we had that solver post-process results on the Sandy bridge and put them up in real time as they were computed on the display. So this capability enables a bunch of interesting options if you want to put the effort into using the devices independently. And then finally you have the mic only, where, native mode that we've talked about. You could also potentially pull off an offload that was essentially almost all mic only if you decided to. But the whole point here is that all of the work gets done on the mic. So how are these things mapped? Well, with the coprocessor only, you end up with MPI on each one of the mics, and all of the communication essentially is done out through, well, in this case, there's actually a layer that allows mic-to-mic direct communication, right? And then you can run whatever threads you want to in each one, okay? So you don't necessarily have to go out through the CPU to get to another mic in the node, but you do to get to the network card. And that's not necessarily always true either if they're all sitting on InfiniBand. So point is, this diagram's a little dated. With the IB support that's in place, the devices can talk directly to each other and not have to stage through the CPU. On the devices, the standard threading models that we've all talked about are there, the Silk Plus, the OpenMP. You can do P-threads if that's your fancy. So it's just any other Linux node. So how do you use this? Well, you'll compile with MPI ICC with a -m mic. Okay, the only difference is that you're using the MPI ICC. And then you have to move it over to the mic in some way. On the TAC systems, they had NFS mounted, so you didn't have to move it directly. And then you can launch it either with an MPI exec from the host, telling it where you actually want to run. In this case, this is the mic's IP address here. Most nodes, at least the nodes at NICs, and I think even these little development boxes, have a host file address entry for these. So you can do things like mic 0 and mic 1 instead of having to know the IP address typically. But that'll be site specific. And if you don't want to launch it off the host, you can actually log in directly to the mic with SSH and you can execute it there, just like you're running on any other Linux node. So when we get to a symmetric model or the asymmetric model, which is the generalization here, you're actually putting a rank on each, in this case, in this picture, each socket and each coprocessor, all right? You could potentially put one rank on a node if you wanted to share the CPU sockets. It's however you choose to map it. It's just MPI, okay? It's no different than dealing with a whole bunch of different cluster nodes, just that they no longer have exactly the same compute capability, okay? So in the generalization down here, instead of having this heterogeneous network of homogeneous nodes that you think of where you're sharing the exact same code across all of the ranks, and here you think of them as heterogeneous ranks, and you do something to differentiate either by ID or communicator or something like that, and you map your problem to it the way you want to. Okay? You're in control completely at this point. So, and in fact, it's probably the easiest way to directly implement the reverse offload model that I mentioned earlier. You can implement reverse offload with the offload pragmas, but it's not nearly as clean, so I would recommend using MPI if you needed to. So how do you use this? Well, you'll just compile both for the host and for the mic, and ultimately I think by the time we reach deployment, we're going to have a unified binary file, right, where the compiler spit out a single binary that runs on any of them appropriately. I've heard talk of this, so my understanding, and perhaps it's wrong, is that that will be there so that you won't have to be quite as concerned about exactly which binary you put where. So in this model, you go ahead and you move the mic executable over to the mic, okay? And then you run the MPI exec off the host, and you specify both the host to run its copy and the mic to run its copy, okay? And you'll find out in a minute, you can also pass environment variables and all sorts of other fun things this way. So then we get to the MPI plus the offload. And in this case, it's more like what you're accustomed to. It's a GPU-based model-ish. You're running with the ranks on the host nodes themselves, and then you just offload as you want to the mics. Well, it becomes interesting, right, if you have, say, one mic and two sockets. How do you control who gets control of the mic and when they do? Okay, so we'll talk about that in a minute, too. So to do this, you just simply compile with the MPI ICC and you run it. Now, with the latest compilers, you actually don't have to specify the offload build. Some of the old compilers you do. So I'm pretty sure that on the two test systems over here, that the compiler's new enough that you don't actually have to specify it. But if you're running at other sites, you might run into a situation where that flag is still required. So, and then you just simply execute it, and the appropriate portions are offloaded. So these are some examples of different ways to offload. You talked about all this yesterday, so I'm not going to go into any real detail about it, but what it boils down to is you can use whichever offload model you want to, whether you're using the MKL or you're using it directly. It all works. So let's talk about hybrid computing, because we've kind of reached a point in time, I think, where it's more or less required to take effective advantage of most of the newest hardware, certainly at scale. So traditionally, we've had MPI as more or less the de facto standard, and you run a rank per node, and everything's homogeneous, and you have one code to keep up with, one parallel model, okay? Well, the problem is we're getting more and more cores per node, and now we've got all these cores on coprocessors as well, right? So the cost of increasing the MPI processes can be tremendous, right? You have issues with overhead due to them being independent processes instead of threads. You can have issues in your algorithm due to the impact of the additional decomposition that you have to do, right? It can be brutal on the convergence rates of some iterative solvers to have to decompose that many times, right? So how do we get around that? Well, we start to incorporate a threading model. We've been talking about it. It shouldn't surprise anybody. And you have your choice of how you want to implement it. But we've kind of reached that point in time where if you haven't started threading your code on nodes, you need to. Okay? You'll definitely see the benefits on the mic. And in fact, most of the folks that run at full scale on machines like Kraken even have to thread on the nodes. It's not because the compute nodes can't handle it. It's because the file system and the network can't handle all of the traffic from 100,000 MPI ranks at once, right? So once again, we need to focus on teaching people to do the hybrid as an appropriate method for parallelism from the start. Okay. And if you do this, because you have as much flexibility as you do with a mic, with the different ways to do the threading and different ways to map things, the offload versus MPI, you can match your actual hardware architecture very closely with your software, and you'll get your best performance when you do. So the options for thread parallelism, these, based on the ease of use and programmer control, you may or may not think that these two should be switched. Personally, this is my view of it. You can have some codes that with the MKL, you just simply link it in and let it do its thing with automatic offloading, and that's great. But the more and more control you want, the more you have to give up in terms of ease, obviously. And so OpenMP is honestly probably the standard that I expect most people who have existing codes to work in. Now, it wouldn't surprise me at all if their codes are restricted to C or C++. If you see some silk making its way in, array notation, some of the pragmas associated with Silk Plus. They're certainly very easy to use, and they get the job done very quickly, if appropriate. But you have to decide whether or not you really want to do that, because Silk, it's tied to the language at this point. There's not a Fortran implementation for it. So, and of course, if you really want to, you can use pthreads. So, how do you actually support how things are mapped when you start doing all these hybrid codes? Okay. Well, you have this MPI pin processor list, which can control where the ranks are mapped to the virtual CPUs in the operating system. Okay. And so you can pin the processors and you can create domains. So for instance, you have rank 0 and it gets these 4 processes, right, which, because of the way they're assigned, happen to be the 4 threads supported by a particular mic core, right? And the idea here is that you really don't want to split your mic cores across different domains. So you can use this to decompose, and then once you've done that, you can control the OpenMP threads with the KMP Affinity variable. Okay. So when you are launching things with MPI exec, you can include environment variables like this MPI pin or the KMP Infinity in between each one of these colon sections, right? And so that applies to that particular host. So you can pass a particular environment to a particular host with a particular binary, right, and a particular number of threads. And so essentially you can run, if you really wanted to, absolutely every rank differently in a fully asymmetric problem, right? So you have complete control, realizing that if this becomes a large problem, this command line is going to grow too long for your shell, right? So you've kind of got a limit with that right now, but in the future there are going to be configuration files that are supported. They're not in place yet, but then you'll be able to specify configs instead of having to give all of this on the command line. So one thing that you really need to think about, because of the particular architecture of the mic and the cost to do the context switching, is to actually make sure that you do specify these things most of the time. You really want to know where you're putting your threads and what they're doing. Okay? Because when you start context switching on the mic, it starts costing a lot. Okay? So the KMP Affinity balanced, it's only supported on the mic, it's not on the Xeon. If you're interested in exactly how all these things place ranks or place threads, then you can look it up in the release notes. But typically, our experience has been that the balanced seems to give the best performance in most cases. So that's kind of our starting point. We go to the balanced first, and then if you have something that's not behaving quite the way you expect it to, you can try some of the others. So recommendations, always explicitly control where you place your threads, okay? And avoid splitting the cores, and you can try the different KMP Infinity settings. And that goes all the way down to literally specifying exactly which OS procs each thread is mapped to for OpenMP, just like you can with the MPI pin domain. So if you decide you want to do that, I included a slide that gives you the mapping for how things are numbered here. If we assume that the mic processor has N cores, then we're going to have 4 N hardware contexts for the threads. And the OS is going to map them in such a way that the 0 proc, which executes most operating system activity, is actually on the very last thread on the mic. Okay? That's done that way to get it out of your way so that you don't actually have to fight with OS contention most of the time. And then the rest of them are just assigned in order after that. So because that OS runs on that proc, you might want to consider avoiding that proc entirely, okay, depending on how much OS activity you're producing. So that's especially important if you're using the offload model, because you can't really control when it's transferring data and what it's doing with syncing and things like that. So the OS activity tends to be less predictable and more intense when you're running in an offload mode. So fortunately, unless you do something to tell it otherwise, the offload compiler, as I understand it, the newest versions actually avoid the OS node, or certainly at least avoid the thread. Okay, so now then, how do we deal with a situation where you have multiple CPUs, multiple sockets, ranks, and they're trying to share a mic? Well, the unfortunate bad news is there's really no way to control that right now. There's not a mechanism. Okay, as far as the operating systems are concerned, they're completely independent tasks by completely different users, basically. And so there's really no way to control them. Unless, of course, you decide to do it the hard way and actually partition your mic using the KMP Affinity or the pin domains such that each rank then gets, say, half of the available cores on the mic, right? But there's really not a good way to say let both sockets have all of the mic when you're offloading. Okay? There's no way to sync that right now correctly. So that's something to be aware of. So that basically covers most of the programming models. I'm going to pause for a minute to see if there are questions before we move on to look at some of the tools. Okay, well, we'll move on quickly because we want you to have time to do the labs. I'm going to tell you up front that I haven't had a chance to play with the trace analyzer on the mic yet. It's been fairly recent that it's been included, and I haven't had a chance to play with it. So I'll give you a little bit of an overview of what it is and what it can do, and then leave you to explore it on your own at some point and ask Intel questions, hopefully, instead of me. Okay? So they provide this very nice little tool that will essentially let you profile across your MPI job. Okay? So it'll show you how the MPI processes interact, and it'll break down the computation and the communication. Okay? It's event-based and it's low overhead, so it scales well. And so you get pretty reasonable results. We did see some folks playing around with it in the lab a couple of weeks ago that I was in. I didn't get a chance to, but my partner did, and he was pretty impressed. So I'm looking forward to this. It does have fail-safe tracing, which is kind of important, and it'll check your MPI, to make sure that things line up the way they're supposed to. And another cool feature that we'll talk about in a little bit is the Idealizer, which will kind of help you remove the machine from the problem so that you can look at just the problems with your code. So the cool thing is the full functionality for this beast is available on the mic right now. If you were going to use it, you have to set up some environment variables appropriately. And you would run with the trace option, okay? And that sets up all the sampling and stuff that it needs for the tracing. And you can control the log file format too. If you use the collect option, it implies the trace and does a full instrumentation of everything. Okay, beware of that. That can generate a whole lot of output for you. Okay, on a huge job anyway. And it also means there's more overhead, so it's more likely to actually perturb the results that you're actually measuring. And then other than that, you just run, just like you normally would. And you can start up the analyzer on your trace file, and you'll get the cool pictures like we were looking at before that you can use. Okay, so let's see. I was expecting the Idealizer to be there. Apparently I missed a slide when I dragged things over. We'll see if it shows up in a minute. It may be out of order. If it's not, I'll give you a brief verbal description. But essentially all it does is it removes all of the network latency and all that sort of stuff from the problem, and it looks at how your code would perform if it could instantaneously communicate. Okay? And so it removes all of the issues you have with contention with other people on the cluster and all this sort of thing. And it looks simply at what sort of delays you have built into your own program. And so it'll give you a timeline just like you saw for the standard trace, and you can use that to try to track down where your problems are. So load balancing. We've said it many times. A mic coprocessor is essentially just a node. except it computes at a different rate than most of the other nodes. So you can run into load balancing problems. I suspect every last one of you in this room is familiar with how to solve this sort of situation, but I'm going to step you through a very quick example that Intel provided. Okay. Short story is, in general, if you have a load balancing problem, there is no magic solution. There's no silver bullet. It depends on how your algorithm is set up as to how you need to go about solving that problem. Okay. And that's one place where the trace analyzer can help. It'll give you a very good idea of where the actual problem is. So in this particular case they wanted to look at, they have this load on the host is too high, and they've got the breakdown with 16 MPI ranks and 1 thread per rank on the host and 8 and 28 on the mic. And so they start to adjust this, and they go to 24 on the mic with 8 threads, and it gets better. And then finally they settle on 12 threads and 16 procs, and you have a really nice balance. Well, that particular benchmark just essentially runs a stencil. So it makes sense that they can balance this. So anyway, here's the ideal interconnect simulator I was going to tell you about. As I said, it got stuck in the wrong place apparently. So what it does is it steps through and traces your application under the assumptions of 0 network latency, infinite bandwidth, no buffer copy time, and an infinite buffer size. Okay, so it's essentially just looking at the handshaking between all your ranks. And so the concurrency is all that really hurts you there. And you know, when it comes to collectives and things like that, they'll show up in this sort of situation. And here's an example. This would be the actual trace that you would see, and that includes all of the network issues and whatever else. And then when you ran the idealized trace, you'd get one that more or less just exposed the problems in your communication pattern within your own program. So that makes it a little bit easier to find and track what you want to look at. And this is just a slide that notes that, essentially as long as the receive shows up after the send, it's assumed that there is no actual time due to latency, and so that adds out to 0. Whereas if the receive comes in before the send, right, then you have to wait. So you can look. This is just showing some of the collective operations and how they would show up, and you can see that it's labeled as to what's going on at each time. And it'll do a breakdown for you that shows you, user type code and the load imbalance portion, right, where things didn't line up right, and then the actual transfer time. And these are the sorts of things that you need to look at if you want to reduce those. And finally, you can even get a breakdown into each individual call. I know this is too small for you to read, but it's like MPI total, MPI receive, and you've got small, medium, and large messages, all reduced, small, medium, and large, all to all V, small, medium, and large. So it gives you some data to give you, an idea of what you need to do to improve your communication patterns within your own algorithm. And finally, we're going to talk very briefly about debugging, and then I'm going to let you get on the labs. So you can set the IMPI debug to have it spit out different levels of information, and you can route that to a file. You can also use the Intel Debugger. Okay, if you're familiar with it, it will run on the mic. You run it on a host, and you can link it to the mic. But it's more or less like you would normally do it. You set up your environment, and you compile the source with the debug flag, and then you execute it, right? And then you go into your debugger, and you can set your breakpoints and that sort of thing. Okay. And in the case of running on the mic, you have to attach it to the mic process. So this is how you have to attach it. You run it and sign things up. But anyway, that's pretty much everything. So I'm going to tell you a little bit about the labs, and then we'll... So, the first lab is essentially just a little prerequisite. It shows you how to set up the environment and that sort of thing. You'll have to do it before you can do any of the other labs. After that, there's just a basic MPI test where it goes out and more or less communicates and does hello world type things. Okay. Then there's a Poisson application that actually uses a red-black Gauss-Seidel solution that you can play around with. And then again, they have a silk implementation of that same algorithm to play with. So, and if you're unfamiliar with the Poisson solve with red-black, there's some information here. But essentially what happens is you end up having boundary conditions and ghost cells, and the ghost cells have to be communicated. And you'll pass over all the reds and compute them. It's entirely independent because the blacks are all lagged a half step, right? So there's no communication. So you can actually communicate your red boundaries while you're computing on the black and vice versa. So that it maps very, very well to a parallel case. I wish it were quite as simple in 3D as it is in 2. And a little bit of information about how the Poisson solver works. If you're interested, you're welcome to read it, but I suspect most folks have probably played with a Poisson solver at some point. So I'm not going to waste any more of your time. The summary is essentially the tools that are available on the Xeon are either available now on the mic or they will be available by launch. So you've got the standard software platform that you're accustomed to with Xeons in full functionality on the mics by launch. So anyway, thank you.